Hello students, welcome to the online class for automobile component design. This subject is present in your 5th semester diploma syllabus for automobile engineering department. Let me first introduce myself. My name is Tanmay Kundu, assistant professor, Department of Automobile Engineering, Dr. Sudhir Chandrasu, Degree Engineering College, Kolkata. Next come to the course objectives. So we have total 3 different course objectives. Coming back to the course outcome, so at the end of this course students will be able to analyze, identify and use these following 4 important course outcomes. So this is our lesson plan. So already I have finished the module number 1. Now today I shall discuss the module number 2, the sub module number 2.5, types of key, design of sunk rectangular key, effect of keyways on strength of shaft. So today's lecture number 16 will basically discuss on the sunk key. So let's begin with the introduction of the key. So what is the key? What is the function of key and how a key can be designed based on the certain guidelines? So a key is a piece of mild steel inserted between the shaft and hub or boss of the pulley to connect these together in order to prevent relative motion between them. So as you know, it's a piece of mild steel that is inserted between the shaft and the hub. So the connection between the shaft and the hub will be completely established, and there will not be any existence of any kind of relative motion between those important components. It is always inserted parallel to the axis of the shaft. So this is very important thing. The key is always inserted parallel to the axis of the shaft. Keys are used as the temporary fastening and are subjected to considerable crushing and shearing stresses. A keyway is a slot or recess in a shaft and hub or pulley to accommodate the key. Next come to the type of key. So the following types of keys are important from the subject point of view. First one is the sunk key, then saddle key, then tangent key, then round key, and finally splines. So total 5 different types of keys are there. So starting from the sunk key. So the sunk key are provided half in the keyway of the shaft and half in the keyway of the hub or boss of the pulley. The sunk key are as the following types. First of all, the rectangular sunk key. So as you know, so this key part looks like a rectangle, so it is called as the rectangular sunk key. So in that rectangular sunk key, the usual proportionals of the key are like width of the key, that is W, should be equal to D by 4. What is D? D is the diameter of the shaft or diameter of the hole in the hub. So W must be D by 4, and the thickness of the key, that is T must be equal to 2/3 of the W. So 2/3 of W means 2/3 of D by 4. So that is D by 6. So the key has, this particular rectangular key has the taper 1 in 100 on the top side only. So here we see this is the taper part, 1:100. Then square sunk key, the only difference between a rectangle sunk key and a square sunk key is that its width and thickness are equal. So obviously we can understand that W is equal to thickness T equal to D by 4. So this is square sunk key. Then parallel sunk key, the parallel sunk key may be of rectangular or square section, uniform in width and thickness throughout. It may be noted that in a parallel key it is taperless and is used where the pulley, gear and other mating piece is required to slide along the shaft. So when there is any sliding motion, we should allow the parallel, we should use the parallel sunk key. And in case of parallel sunk key, as the name suggests, the two lines must be parallel. That means there is no case of tapering. Give head key, it is a rectangular sunk key with a head at one end known as give head. It is usually provided to facilitate the removal of the key. A give head key is shown in figure A and is used in shown in figure B. So this one is the taper 1:100. So this one is the give head key, as you know. The angle is 45 degree. The usual proportions dimensions are provided like this. This one is the shaft, this is give headed key. Tapering is 1:100. The usual proportional give head key are like width u shall be w equal to d by 4 and thickness shall be equal to d by 6. Next come to the feather key, a key attached to one member of a pair and which permits the relative axial movement is known as the feather key. It is a special type of parallel key which transmits a turning moment and also permits the actual axial movement. It is fastened either to the shaft or hub, the key being a sliding feet in keyway of the moving piece. So here you see this is the feather key. The feather key may be screwed to the shaft as shown in figure A, or it may have double give head as shown in figure B. Okay, so here we see the various proportional feather key of rectangular sub key are like this. So the dimensional proportionals are very much similar in case of feather key, like the rectangular shank key or give head key. That is, W should be equal to d by 4 and T shall be equal to d by 6. Next come to the Woodruff key. The Woodruff key is an easily adjustable key. It is piece from a cylindrical disc having segmental cross section in front view as shown in figure. The Woodruff key is capable of tilting in a recess milled out in the shaft by a cutter having the same curvature as the disc from which the key is made. The key is largely used in machine tool and automobile construction. So this one is the Woodruff key. Next come to the relative advantages of the Woodruff key, like it accommodates itself to any taper in the hub or boss of the mating keys. It is useful on tapering shaft end. Its extra depth in the shaft prevent any tendency to turn over in its keyway. Now come to the disadvantage. The depth of the keyway weakens the shaft. It cannot be used as feather. Next come to the saddle key. The saddle key are as following two types: flat saddle key and hollow saddle key. So a flat saddle key is a taper key which fits in a keyway in the hub and is flat on the shaft as shown in figure. So like this. This is a flat saddle key. It is likely to slip around the shaft under load. Therefore, it is used for comparatively light loads. And what about the hollow saddle key? So it is a taper key which fits in a keyway in the hub and the bottom of the key is shaped to fit the curved surface of the shaft. Since the hollow saddle key hold on by friction, therefore these are suitable for light loads. It is usually used in temporary fastening and fixing and setting eccentrics and cams, etc. This is saddle key. Next come to the tangent key. The tangent key are fitted in pair in right angle as shown in figure. Each key like this, this is a tangent key. This is a tangent key. Each key is to withstand torsion in one direction only. These are used in large heavy duty shafts. Next, round key. The round key as shown in figure, this is the round key, are circular in section and fit into holes drilled partly in the shaft and partly in the hub. So here you see this particular tapering pin is pushed into the hole partly in the shaft and also into the shaft, into the hub. They have the advantage that their IOS may be this is keyway. Their keyway may be drilled and rimmed after the mating parts have been assembled. Round key are usually considered to be most appropriate for lower power drives. So these are the different round keys. Sometimes the tapered pin as shown in figure is held in place by the friction between the pin and the rimmed taper holes. This one is the taper pin. Spline. Sometimes keys are made of integral with the shaft which fits in the keyways broached in the hub. Such shafts are known as the spline shaft as shown in figure. These shafts usually have 4, 6, 10 or 16 splines. This one is the spline shaft. This is the integral part of the shaft. The spline shafts are relatively stronger than shafts having a single keyway. The spline shafts are used when the force to be transmitted is large in proportion to the size of the shaft, as in automobile transmission and sliding gear transmission. By using splined shafts, we obtain axial movement as well as the positive drive is obtained. Next, what are the different forces acting on a sunk key? When a key is used transmitting torque from a shaft to a rotor or hub, the following two types of forces act on the key. First force is the force that is F1 due to fit of the key in its keyway, as in a tight fitting straight key or in a tapered key driven in a place. These forces produce compressive stress in the key, which are difficult to determine in magnitude. Then force F, that is due to the torque transmitted by the shaft. These forces produce shearing and compressing or crushing stress in the key. The distribution of the forces along the length of the key is not uniform because the forces are concentrated near the torque input end. The non-uniformity of distribution is caused by the twisting of the shaft within the hub. The forces acting on a key for a clockwise torque being transmitted from a shaft to a hub as shown in figure. This one, we see these are the different types of forces on sunk key. In designing a key, forces due to fit of the key are neglected, and it is assumed the distribution of the force along the length of the key is uniform. Next, we have to determine the strength of a sunk key, a key connecting the shaft and hub as shown in figure above. So T means it is the torque transmitted by the shaft. F means this is the F. F means it is the tangential force acting at the circumference of the shaft. This is the F. D means diameter of the shaft. L means length of the key. W is the width of the key. This is W. T means thickness of the key. This is thickness. Sigma and tau C. Sorry, sigma C and tau. Sigma C means it is the crushing stress, and tau means it is the shear stress for the material of key. A little consideration will show due to the power transmitted by the shaft, the key may fail due to shearing or crushing. Considering shearing of the key, the tangential shearing force means that is capital F. This is the capital F. This is the tangential shearing force acting on the circumference of the shaft, so that may be force equal to area into stress, that means area resisting shearing multiplied by shearing stress. So L into W into tau. So therefore torque transmitted by the shaft shall be T equal to F into dy 2. So L into W into tau into dy 2. Now considering crushing of the key, the tangential crushing force acting on the circumference of the shaft, so it will be F equal to area resisting crushing into crushing stress. Now what is that area? So L into T by 2. This is L and into T by 2. So this is the area resisting the crushing. So torque transmitted by the shaft, that will be T equal to F into d by 2. That means L into T by 2 into sigma C into d by 2. The key is equally strong in shearing and crushing if, that means the torque due to shearing is equal to torque due to crushing. That means L into W into tau into d by 2, that is the torque due to shear, and this is torque due to crushing. So finally we get the relation W by T equal to sigma C by 2 tau. Now the permissible crushing stress for the usual key material is at least twice the permissible shearing stress. So therefore from equation 3 we can write that we have W equal to T. As we know that here we have got that sigma C is equal to 2 times of tau. So just sigma C equal to 2 times of tau. So sigma C by 2 tau equal to 1. So put that thing, so it will come W equal to T. That means it is coming as a rectangular square sunk key. So in other words, a square key is equally strong in shearing and crushing. In order to find the length of the key to transmit full power of the shaft, the shearing strength of the key is equal to the torsional shear strength of the shaft. So we know that shearing strength of the key, that should be T equal to L into W, that means the torque due to shear, that is L into W into tau into d by 2. And also we know torsional shear strength means T equal to pi by 16 tau 1 d cube, where tau 1 is the shear stress of the shaft material. So balancing this equation 4 and 5, we get this particular relation like L equal to this one. So 1.571 d into tau 1 by tau. When the key material is same as that for the shaft, so therefore what will happen, tau will be equal to tau 1, that means L equal to 1.571 d. Okay, this is a very important relation. So let us solve one numerical for key design. So design the rectangular key for a shaft of 50 mm diameter. The shearing and crushing stresses for the key material are 42 MPa and 70 MPa. So what is the given data? D is given, shaft dia 50 mm, tau, that is the shearing stress, is given 42 MPa, that means 42 Newton per millimeter square. Crushing stress is given 70 MPa, sigma c equal to 70 Newton per millimeter square. Now the rectangular key is designed as discussed below. Now we have a table. From this particular table 13.1, although this table is not attached, but in any book especially you can find this particular table, although I shall give you the this particular table at the very end of this lecture. Also I shall attach it along with that. But for the for any shaft with 50 mm diameter, the width shall be taken, width of the key shall be W equal to 16 mm, and thickness of the key should be considered T equal to 10 mm. Now we know that W equal to d by 4, from the previous things we have come to know W equal to d by 4. D is given 50, so 50 by 4, that means 12.5, so it can consider nearly equal to 16. Also we know that T, that is the thickness, equal to d by 6, so D is given 50 divided by 6, so it means it is equal to 8 almost, so it can be taken nearly equal to 10, like this. The length of key is obtained by considering the key in shearing and crushing. So let L equal to length of the key. So considering the shearing of the key, we know that shearing strength or torque transmitted torque transmitted by shearing, so it will be T equal to L into W into tau into d by 2. So put all those things, finally we get 16,800 L Newton millimeter. Similarly, torsional shear strength is equal to T equal to pi by 16 tau dq. So putting all those value, we get this relation. So balancing these two equations 1 and 2, we get L equal to 61.31 millimeter. Now as this is the case of shearing, now consider the crushing. So in case of crushing, we know that torque transmitted due to crushing will be equal to L into T by 2 into sigma c into d by 2. Put all those things, so we have got 8750 L Newton millimeter. So from equation 2 and 3, that means this is the equation 2 and this is equation 3. So balance this equation 2 and 3, we get L equal to 117.7. So taking the larger one, so first of all we have got L equal to 61.31 considering the shearing, and L equal to 117.7 considering the crushing. So we will take the greater one. So finally that L can be selected as 120 millimeter. Next come to the effect of keyway. So a little consideration will show that the keyway cut into the shaft reduces the load carrying capacity of the shaft. This is due to the stress concentration near the corners of the keyways and reduction in cross section area of the shaft. In other words, the torsional strength of the shaft is reduced. The following relation for the weakening effect of the keyway is based on the experimental result by H.F. Murray. So E equal to, it is coming like E equal to 1.02 within into W by D minus 1.1 into H by D. So here E is equal to sap strength factor. It is the ratio of the strength of the sap with the keyway to the strength of the same sap without the keyway. So W is width of the keyway, D is the diameter of the sap, H equal to depth of keyway. Generally it is taken as thickness of the key divided by 2, that is T by 2. It is usually assumed that the strength of the key's shaft is 75% of the solid shaft, which is somehow higher than the value obtained by the above relation. In case of the keyway is too long and the key is sliding type, then the angle of twist is increased in the ratio k theta as given by the relation. So this relation also coming like k theta equal to 1 plus 0.4 W by D plus 0.7 into H by D, where k theta is the reduction factor for angular twist. Now based on that keyway we can solve one numerical. A 15 kilowatt 960 rpm motor has a mild steel shaft of 40 mm diameter and extension being 75 mm. The permissible shear and crushing stresses for the mild steel key are 56 MPa and 112 MPa. Design the keyway in the motor shaft extension. Check the shear strength of the key against the normal strength of the shaft. That means what are the different data? So given data, power is given 15 kilowatt, that means 15 into 1000 watt. RPM given 960 RPM. D, that is the shaft diameter 40 millimeter. Length is given 75 millimeter. Tau is given, shear stress is given 56 MPa. Sigma C, that is the crushing stress, is given 112 MPa. Now we know that torque equal to power divided by angular velocity. So power divided by 2n pi by 60. So from this relation we get the value of the torque T. Okay, so let W equal to width of the keyway or key. So considering the key in shearing, we know that torque transmitted by shearing. So T equal to L into W into tau into D by 2. So from this expression put all those data. So we get width of the key as 1.8 millimeter. The width of the keyway is too small. The width of the keyway should be at least D by 4. So D means it is given 40 divided by 4, that means 10 millimeter. So we will consider the keyway width as 10 millimeter. This is the answer. Since sigma C equal to tau, as we know in case of key whatever we design that crushing stress, here we see the crushing stress is always taken 2 times of the shear stress. Here we see crushing stress is like 112 MPa and sigma C tau is given 56. So the crushing stress, that means sigma C equal to 2 times of tau. Therefore square key of W equal to 10 millimeter and T equal to 10 millimeter is adopted. Okay, so this is the condition for the square key, as we know. So in case of square key, that sigma C is 2 tau, so W will be equal to T and equal to 10 millimeter. So as per H.F. Murray, the shaft strength factor will be from that formula equal to 1.02, 1 minus 0.2 W by D minus 1.1 into H by D. So put all those data, finally we get like E equal to 0.8125. So strength of the shaft of the key will be it will be just reduced. So reduced by how much? It will be reduced by 0.8125, like multiplied by 0.8125. So it is coming like 571844 Newton. So and shear strength of the key, what will be the shear strength of the key? So it will be L into W into tau into D by 2. So it is 75 into 10, finally putting all those. So we have got the shear strength of the key. So it is coming the reduction factor like as per the previous formula. So check the shear strength of the key against the normal strength. So here we see, just we will take the ratio, that is shear strength of the key divided by normal strength of the shaft. So shear strength of the key, it is coming 84084 into 10 to the power 4. That is the shear strength of the key. And what is the normal strength of the shaft? So normal strength of the shaft is like this, 571844. So it is, the ratio follows 1.47. So shear strength of the key is 1.47 times of the normal strength of the shaft. So this is all about my today's lecture on key and key way. So please go through all the study materials thoroughly and practice some numericals as available in your textbook. So thank you very much.